Hi there, I'm talk about liquids this time. So if you've ever seen videos about how lava moves around, it flows and oozes, it's super hot, and then after a while, after it cools off, it turns into a rock. So we can have anything on the planet can turn into a liquid if it's hot enough. So even rock can turn into a liquid. So what factors determine the physical properties of a liquid? Substances that can flow are referred to as fluids, and liquids and gases are both fluids because they can flow. You can pour them. So that's what flow means. So there's two things going on. You're going to have motion of particles in a liquid, and you're also going to have attractions of those particles in the liquid. So those are the two things that are happening when we're talking about liquids. So what's the relationship between evaporation and kinetic energy? You know that when things go from liquid to gas, it's called evaporation. And kinetic energy, remember, is moving. So the conversion of a liquid to a gas or vapor is called vaporization. We're changing liquid into a vapor. When that happens at the top of a liquid, it's called evaporation. So same idea, but at the very top, we're specifically calling it evaporation. So if you have an open container, the molecules can evaporate and escape from the container. So we're having things evaporate. We're having this liquid all bouncing around and touching each other, and they're all physically touching each other. But when they get enough kinetic energy, moving energy, they can pop off the surface and go into the gas phase. So that's called evaporation. If we have a closed container, like this cute little greenhouse, we can have the liquids moving around. And then some of them get enough energy, kinetic energy, to jump into the gas phase. Then when they get enough of them together, they can lose their energy and start collecting near each other and then turning into a drop and then coming back in. Then they're going to collect as a vapor above. And then some of them are going to lose all that energy because they've been clumping together and they're attracted to each other, and then they start going back down into the container. So they're condensing back into liquid. During evaporation, only those molecules that have that minimum kinetic energy, have enough energy to escape, can jump up into the gas phase. So when can we have that going back and forth between liquid and vapor, like I've shown you in the greenhouse? So when the vapor pressure is a measure of the force exerted by a gas upon a liquid. So it's how much vapor is over the top of the liquid. When there's enough of it, that pressure is high enough, it will condense back inside and go back into liquid. So we'll go liquid, will evaporate to gas, then there'll be a loss of that kinetic energy, and then those gas particles will slow down and condense and go back into the liquid. So when we have things going back and forth between liquid and vapor to liquid, it's called dynamic equilibrium, because the number of particles that are jumping up into the gas phase is equal to the number of particles of gas phase turning back into liquid. That's called dynamic equilibrium. If we increase the temperature of a contained liquid, it increases the vapor pressure because we're giving more kinetic energy to the particles, and they can bounce up into the gas phase. Particles in the warm liquid have increased kinetic energy, like I said, and so you'll have more of them jumping up into the gas phase. Here's some vapor pressures of, this is how much, it's kind of like a measurement of how much vapor we have over the top of a liquid. So you have that closed greenhouse container with a little cup of water inside. So the hotter you get the temperature of that greenhouse, the more you're going to have the gas particles jumping up above the surface. And you'll notice that if we have these three different molecules at the same temperature, that this one here wants to be a gas much more than the water does. Water is attracted to each molecule is attracted to another water molecule. So these do not want to jump up into the gas phase as much as ethanol, which is the alcohol, the drinking alcohol in mixed drinks and beer and wine. And then diethyl ether. So ether is very, very, very wanting to stay in the gas phase because it's not attracted with another diethyl ether. So water is attracted to itself, ethanol less so, diethyl ether, the least of all of these. So you can tell that if you're given three vapor pressures of different molecules, you can tell who is attracted more to itself. It's a good measurement of that. We can measure vapor pressure. We talked about using a barometer for atmospheric pressure. We can use another similar instrument called a manometer to measure the vapor pressure over during a lab experiment. So here we have an example. We have the ethanol we just talked about. We put a manometer, we put some mercury-filled tube attached to this ethanol, and we can see how much that ethanol is pushing that mercury up. So it's got a vapor pressure right here of this amount. If we have, that was 0 degrees. If we increase the kinetic energy by changing to 20 degrees, we can make that vapor pressure get higher. So this is a good measurement that we use in the lab to see how much we've changed atoms or molecules to the gas phase. So what is boiling? Let's talk about that. When we heat a liquid to a temperature at which the particles, you have particles that have enough kinetic energy to vaporize, we're starting to boil. So you'll see the little bubbles when you heat up water on the stove. Those little bubbles are boiling. So when the temperature at which the vapor pressure of the liquid is just equal to the external pressure, it's called the boiling point. And so it's a temperature number that we talk about when we talk about boiling point. So for water, it's 100 degrees at 760 millimeters of mercury. So we have different liquids will boil at different temperatures because we're trying to get to that vapor pressure. And if we reduce the pressure pushing down on the molecules over the surface of the container, then we will have a lower boiling point. We'll make it harder for those atoms to pop off the surface. So at a lower external pressure, when we have less pressure pushing down, the boiling point will decrease. If we have more pressure, the boiling point will increase. We'll need more temperature, more kinetic energy from the stove to push on the molecules in the liquid phase to jump up into the kinetic, to have enough kinetic energy to jump into the gas phase. So altitude will affect your boiling point. If you're at sea level and you have 101, remember that standard pressure pushing down. Bubbles of vapor cannot form in the water. It does not boil. But once we get to 100 degrees, then we have enough of the kinetic energy for those liquid molecules of water to jump into the gas phase, so you see bubbles. And so then you'll have the boiling start. If we're at on top of Mount Everest, remember there's less pressure pushing down. So there's going to be enough kinetic energy for these molecules of water to change into the gas phase because there's less stuff pushing down on them. They have less pressure pushing down on them, so they're able to form into bubbles and escape. So that's when you have boiling. So you're going to have a lower boiling point at Mount Everest. You'll have a lower temperature for boiling. That's called the boiling point. So people who live like in Denver, they have troubles with cooking because of this. They can't get their temperature of their water high enough to do what they need to do. So some people who are baking a cake in Denver have to adjust their baking parameters so that things will work out right. So they're going to have a much different temperature for boiling when you're at high elevations. Here's vapor pressures for different things. So you see that at various temperatures. So for example, let's look at this temperature here. Let's look here. At 60, this molecule has a lower vapor pressure than water. So that means that this guy likes to hold on to each other. They're very attracted to each other compared to water. And then ethanol has less attraction to each ethanol molecule to another ethanol molecule, so it can boil. And this chloroform has even less attraction to another chloroform, so it can jump up into the gas phase. So the attractiveness of molecules for each other will affect the boiling point. So the normal boiling point that what we talk about, the word normal means that we're standardizing this pressure to 101. That's that standard pressure. When you have that standard pressure, then you have something called the normal boiling point. So we measure all boiling points at a standard pressure because of that change that we were talking about. So here's boiling points of different things. So these ones take a lot less energy to get them to jump into the gas phase compared to water. Water's really each water molecule is really attracted to another water molecule next to it. So it takes a lot more energy to bounce it up from liquid into gas. Let's see how much you got out of this section. Good luck. So in liquids, the attractive forces are, what do you think? So they're strong enough to keep the particles closer together than in the gas phase. So they're attracted to each other in liquids. Which of the following is a process that absorbs energy? So this is a really good question. So think about this one. This would be a really good test or quiz question. So it takes energy to make those liquids jump up into the gas phase. So this process change absorbs energy. In a sealed gas liquid system at constant temperature, eventually, this is that greenhouse we were talking about. What do you think? So the rate of evaporation is going to equal the rate of condensation. It's in dynamic equilibrium. All right, so I hope you learned something from this section. I'll talk to you soon. Bye-bye.